My name is John Heisman, and I work for NGS Software, based out of London. I've given a couple of talks before at BlackHat. This is my first talk at Vegas. If you've seen any of my other work, to quote The Simpsons, you may remember me from such talks as implementing and detecting ACPI BIOS rootkit, and its much anticipated sequel, implementing and detecting a PCI rootkit. Today I'm going to talk about the extensible firmware interface. I certainly know that some of you in the audience are very familiar with EFI. Others, I guess, will, from using a MacBook, for example, will have a passing knowledge of it. And I suspect some of you may have heard of it but aren't exactly sure what it is, or at least some of the details of how it's implemented. So this is what I want to cover today. Actually, I'm going to start this talk by talking about the legacy BIOS, the traditional BIOS. So we're going to talk about the function of the BIOS on non-EFI systems, older systems. We're going to talk about means of attacking traditional BIOSes, since many of these are applicable to EFI. We're going to talk about the limitations of the legacy BIOS just briefly, because this provides us with some motivation for why Intel started to develop a replacement. I'm then going to briefly introduce the EFI environment. We'll cover the major components. We'll then move on to means of attacking the EFI environment, and we'll make reference to the attacks that we talked about for the legacy BIOS. I then want to talk about the successor to EFI, UEFI, and what the future holds. And we'll draw some conclusions off that. Firstly, some caveats about this talk. Most of my talks regarding rootkits have not been about what the rootkit actually does. I'm more concerned about means of persisting a rootkit, or even just some malware. And I'm concerned about persisting it in such a way that we can subvert the operating system as it's loading. So I'm not going to talk about the actual specifics of the rootkit that I refer to. In general, the rootkit I refer to is simply a rootkit that subverts the kernel in some way. So it may manipulate kernel data structures, it may simply patch functions in the kernel to provide a backdoor. Second caveat is that this talk isn't about trusted computing, though I will make mention to it. The EFI spec certainly doesn't mandate that you have to have a TPM, for example, in your system. And when I started looking at EFI on a MacBook, my MacBook doesn't have a TPM. So whilst, as I said, I'll make reference to it, it's not critically important. Some of these attacks will require physical access when we talk about flashing firmware, for example. Some devices, depending on the device, require flipping a jumper. Almost all of these attacks, I'm not going to talk too heavily about how we actually carry out the attack from its initial concrete implementation. Simply the ability to flash firmware. Most vendors have a number of tools available to do this. Reverse engineering those tools or just downloading chipset specs will give you that information. Most of these attacks could be implemented as a blended attack. So, for example, we chain a bug in a browser. So a user visits a malicious website that owns the browser. If they're running as admin, that's great. We can typically load a driver on most systems. Obviously, 64-bit Vista we can't, unless it's signed. So we may need, if we're not running as admin, we may need some sort of escalation to admin, or ideally an escalation from user mode to kernel mode. And then we can target the firmware. And I'd also like to say that parts of this research are definitely still work in progress. EFI is a complex beast, and UEFI is also very interesting. And I apologize that there's no white paper in the BlackHat handouts. If you'd like to check the NGS software website in about a month's time, then I'll have a white paper up there that covers all of this and actually goes into some more detail on some of the attacks. So let's briefly go over the role of the BIOS. When you turn your system on, The CPU starts executing from a fixed address, a reset vector, and ultimately it doesn't know anything about your hardware. First thing it must do, the firmware must do, is initialize the memory controller, the north bridge, and the south bridge so that we can actually start talking to devices on the bus, on PCI bus, for example. The second thing it will typically do is, as we get going, it will locate option ROMs. So PCI devices on the bus typically have an expansion ROM, a ROM that is scanned for by the BIOS, copied into physical memory, and then executed from physical memory. So, for example, your video card has an expansion ROM or an option ROM. I'll use those terms interchangeably. The BIOS also provides some means of user configuration. So, for example, the familiar setup screen where we can configure hardware, and we can also configure the boot device priority, so we can choose a hard disk to boot off. And we can also persist those settings to some non-volatile RAM. And finally, the BIOS will launch the bootloader. Actually, that's not strictly true. It will simply launch whatever's hooked in 19. But in most circumstances, we'll want to load the bootloader, which will then load the operating system. Some means of attacking a legacy BIOS. We can simply modify the BIOS code itself and then reflash the firmware. The way this attack would work is that we'd obtain a BIOS typically from a vendor website. This is after we've done our due diligence on the system that we've attacked. So typically we'll have compromised the system, we'll have determined what hardware it is, what chipset, motherboard, etc. We will then visit vendor's website, get a reference, get an implementation of the BIOS, download that BIOS. Typically the BIOS will be compressed data. When we decompress it, we'll find that it's a collection of code modules and data modules. We can start disassembling some of the code modules, patch them, compress it back up, and just use standard flashing tools or our reverse engineered equivalent of those tools to flash it back. Second option is that we can modify PCI option ROMs, so we can actually flash the firmware on PCI devices. And as I briefly mentioned on the last slide, during a power on self-test, the BIOS will actually copy those option ROMs into RAM and execute them, so our code gets executed in the BIOS. Third option is we can modify the advanced configuration and power interface tables. These will basically be one of the data modules in the BIOS, and I'll talk more about ACP attacks later. And fourthly, we can carry out some non-persistent warm reboot attacks. So by non-persistent, I mean essentially when we power off the system, we essentially lose our rootkit. But as long as we keep warm rebooting the system, we stay in memory. How might we go about patching the BIOS? Well, to be honest, there's a ton of places we can insert code. But ultimately, our goal is to subvert the bootloader. Bootloader is responsible for loading the kernel. So if we have code executing inside the bootloader, then it's a short step to patch the kernel. In a legacy BIOS, the bootloader must rely on a set of services exposed by the BIOS. And this is through the interrupt vector table. So this is the x86 real mode interrupts model. And basically, the IVT is built up dynamically. So, for example, things like a video card will basically register that it's the handler for int10 hex video. As I've already mentioned, the BIOS will call the bootstrap loader vector, which is int19 hex. So just when it's leaving, when it's about to launch the bootloader. So ultimately, an attack here is that we just need to find where it passes off control, where it calls int19, and we need some code before that modifies the IVT, and we basically hook an interrupt. On my next slide, or in a couple of slides' time, I'll talk about what interrupt we might choose. But it's a fairly simple process. Some caveats, as I said, it may require physical access, and also this attack assumes that we don't require signed updates for firmware. I'll elaborate a bit on PCI option ROMs. So the ROMs on PCI devices hold initialization code, and most likely this code is x86 code. And during the post, it's simply copied to RAM and executed. And typically it's stored in an EEPROM or an EEPROM, the difference being whether we need to actually remove the chip to flash it or whether we can do it while it's on the card itself. An example here is if you buy a PCI Express graphics card, then typically you'll have an EEPROM on it. And if you dump the ROM off that card, you'll find that it will hook int10, and this is to implement VGA and VBE BIOS functions. And actually, a clarification when I talk about PCI, ultimately I'm using that term to mean PCI, AGP, and PCI Express, because the option ROM mechanism is the same. How we'd attack an option ROM. Obtain the option ROM. This is pretty easy. We can either go to the vendor's website and download latest version, or we can just rip the ROM directly off the card. If you look at the PCI spec, it talks about how to actually program the card so that you can dump the ROM into physical memory, so we contain an exact image of it. Flashing is pretty easy. We simply need to do I/O to the card. Again, the way I would do this is start by finding the vendor's tool to actually do this and reverse engineer it. Patching the option ROM, again, we're going to target the IVT, and we want to hook an interrupt, and when the bootloader calls that interrupt, we then have the ability to patch the kernel or kernel modules. So to answer the question of which interrupt to hook, well, EI produced a boot sector rootkit, and they took the route of hooking int13 hex, as in disk. So basically, every time int13 was called to load a kernel module, or the kernel itself, then essentially they would filter the data coming back and look for a particular byte stream and just patch it on the fly. When I talked at BlackHat DC about PCI rootkits, I chose int10 hex video as my target interrupt. And this was a Windows-specific technique because I noticed that the Windows kernel actually calls int10 fairly late in the boot. And the reason it does this is it switches into V8086 mode, because obviously the Windows kernel runs in 32-bit protected mode. And so essentially, in order to call int10 in the real mode interrupt vector table, it's necessary to switch into virtual 8086 mode. So switch the processor into that mode and then execute my code, execute the int10. And because I've hooked that int10, I can detect this case. And ultimately, I was able to influence the context structure that the operating system used to return from V8086 mode. Ultimately, there are likely to be other candidate interrupts that you can hook. The legacy BIOS, as I said, the bootloader relies on services exposed by the legacy BIOS. So ultimately, it's at our mercy. Pros and cons of option ROM attacks. One of the benefits is you typically don't have any write protection on the cards. As I said, flashing is pretty easy. We just need to do a few I/O instructions to the card. Almost all things like graphics cards these